The significance of fission was lost by no country, not on either side of this incipient war. The first Heisenberg report came on the 6th of December 1939, just a few months after fission had been discovered, when Heisenberg wrote to the Armament Authority and said that a fission nuclear reactor was feasible. Uranium would consist of the enriched form, that is to say, the kind of uranium where the total number of neutrons and protons added up to 235, not the much more common 238, and that this uranium-235 would make a powerful new explosive which surpasses the explosive power of the strongest explosive material by several orders of magnitude. Heisenberg said you would have to moderate to slow down the neutrons to make them cause fission by some kind of heavy water, that is to say, ordinary water with extra neutrons, or graphite. The geometry of the whole thing he considered a spherical form or a cylindrical form, and he added that the separation of this uranium-235, which is less than 1% of the kind of uranium that you found in the ground ordinarily, for power was really going to be difficult. He calculated the need for tons of this uranium-235 in order to be able to get a reactor to really work. His second report, in February of 1940, was one where Heisenberg judged that graphite could not be used as a moderator to slow down the neutrons to allow them more easily to cause fission. This was confirmed by quite a good experimentalist, Walter Botha, only because the German experimentalists couldn't get the kind of pure graphite that they wanted, and the industrial grade that they had so many impurities that it seemed to confirm Heisenberg's judgment that graphite couldn't be used. If you couldn't use graphite to slow down the neutrons to make them more likely to cause fission, it meant you needed heavy water, that is to say, the hydrogen with extra neutrons attached to the oxygen, and that this could be used to slow the neutrons down. So where do you get the heavy water? Well, that they subcontracted to a plant in Norway. In February of 1942, the German Army Ordnance decided that nuclear weapons were simply not going to be part of the war because it was so difficult to produce the amount of uranium-235 that was needed. It would have been on a huge scale, roughly on the scale of the entire rocket program that the Germans were building, say a couple of $billion in 1945 equivalent. Or you had to be able to separate out plutonium, an element 2 above uranium on the periodic table, which also seemed incredibly difficult. So on both counts, German Army Ordnance decided that nuclear weapons were simply going to be out of the question. But to advance the project in any way to move it forward, they needed this heavy water. And the plant that was designed to produce it, Norsk Hydro, was destroyed by sabotage after several very, very difficult attempts to destroy it. It was finally wrecked on the 27th of February 1943. The Germans had rescued a certain amount of the heavy water and were trying to ship it back to Germany when, again in an act of sabotage, the Norwegian resistance sunk a ferry with a full supply of heavy water on the 20th of February 1944. With that sinking, it almost became impossible to go forward in this project. But the Germans had achieved certain successes. In 1941, part of the project in Leipzig achieved some part of a chain reaction. They discovered that plutonium was an alternate way of building an atomic bomb other than the separation of this lighter isotope of uranium, uranium-235. They'd gotten the backing of certain parts of industry and the German army, and success looked like it might happen. But there followed a lot of conflict inside the German project itself about how far a neutron could get before it interacted by splitting a uranium nucleus, how much uranium you needed to go critical. Did you need tons, or did you need only a certain number of kilograms? What kind of moderators could you use? They'd ruled out graphite. They needed the heavy water. They couldn't get the heavy water. So there were many things that impeded the German project from getting very far, but it had gotten a start. Heisenberg, on February 26, 1942, met with German ordnance and said this: if one could assemble a lump of uranium-235 large enough for the escape of neutrons from its surface to be small compared with the number that actually causes more fission, then the number of neutrons would multiply enormously in a very short space of time. The whole uranium fission energy of some 15 million calories per ton would be liberated in a fraction of a second. Pure uranium-235, Heisenberg told the military authorities, is thus seen to be an explosive of quite unimaginable force. So it wasn't for lack of understanding that this could be a weapon and a source of power. It wasn't for lack of understanding that plutonium and uranium-235 were the right substances to look for. It was the scaling up that made it impossible for the Germans to proceed, coupled with misassessments of what graphite would be, what the free path of a neutron would be before it interacted, of the amount of the critical mass necessary, of the need to have very fast neutrons causing this explosive reaction, and therefore making it different from the kind of multiplication that would occur in a reactor where you want things to proceed in a controlled and slower fashion. So there were many aspects of the problem that ground it to a halt. But Heisenberg continued to rise in the hierarchy of German physics. In June of 1942, he was promoted. He defeated certain attempts to describe him as a white Jew, as some of the Aryan physicists were wont to call him. He had family relations with Himmler, who was able to clear his name and to tell the attackers to back off in their criticism of Heisenberg. Heisenberg went on to lecture about these questions of nuclear physics and possibly generating power or weapons. He briefed Albert Speer, the architect of the Third Reich, and other military commanders on the 4th of June, 1942. He briefed dignitaries at Hermann Goering's Aeronautical Research Academy in May of 1943. But both indicated that the reactor and the bomb had problems. Each dampened expectations for a rapid solution to be conducted inside the course of the war. For all these reasons, the Nazi bomb never advanced very close, or even remotely close, to actually building a workable bomb. But they did make steps towards making a reactor. They had formed pieces of it, and in fact, we can take a look at one of the chunks of uranium that had been used to try to build one of the reactors that Heisenberg supervised, and that was hidden but eventually discovered by an American mission that had been sent to try to capture what was known by the Nazis of their project. And they rounded up the physicists who were sent to a place called Farm Hall in Kent, in England. They captured the pieces of the reactor, and they found masses of documents that surrounded the project, which the Germans had hidden. One of the great propulsive forces of the Manhattan Project was the enormous fear that the British and the Americans had that the Nazis would get the atomic bomb first. After all, fission had been discovered in Germany by Hans Strassmann, and before she was fleeing for her life, Lise Meitner. And their goal, the goal on the American and British side, was to get this bomb as quickly as possible. But part of that effort meant finding out exactly how far the Nazis had gotten. They had developed, as we know now, these enormously capable weapon systems of the rockets, the V-2s, the cruise missiles, the V-1s, swept-wing jets by the end of the war were in the air and fighting. The Nazis had a tremendously active weapons program of advanced technology. So it seemed entirely possible that they were building an atomic bomb. Some of the physicists there, like Hahn, were clearly still in Nazi Germany, so was Heisenberg. And between them and the many others that they'd recruited to the project, there was a real fear on the British and American side that they'd actually gotten ahead of the Americans. So a mission was formed, headed by a guy named Pash, who had been in counterintelligence in the United States and attached to the Manhattan Project, and Samuel Goudsmit, a physicist who had discovered electron spin and contributed enormously to our understanding of the atom. So they formed this group, And right behind, and sometimes even ahead of the advancing troops across Europe, they went to Italy, and then as troops fought their way across Europe, they would go from country to country, in Belgium, for example, and in France, and eventually in Germany, trying to figure out how far the Germans had gotten with chemical and biological weapons, but most importantly with the atomic bomb. Finally, the German scientists were discovered one by one. They had a list of people they were looking for. Some of them had disguised themselves as medics, some of them were on the run, and they were captured, along with the documents and indeed the reactor that the Germans were working on. One of the pieces of that reactor was seized by Edwin Kemble, a spectroscopist and physicist at Harvard, and he brought it back, and that's what you see here is a piece of uranium from the reactor at Haigerloch in southern Germany. Uranium is quite an astonishingly heavy substance, so one of the first things you can do is to see an identically shaped block. This has got a little lead shield around it, but it doesn't even begin to tip the scales, and you have to keep adding weights, these kilogram weights and other weights, to even approach the weight of the uranium. So uranium is very dense. It's also, of course, radioactive, and you can see that, which is why I'm not going to touch it with my hands. And these uranium blocks were being used to try to develop to get the reactor to actually produce a sustained chain reaction. It never was a very sustained one. They got indications of a chain reaction earlier on in the war, and they really made no progress in any substantial way towards building an atomic bomb. The scale of Los Alamos was several $billion. It was the scale on the Nazi side of the V2 program, the rocket program, which involved hundreds of thousands of people. So it was nowhere near that. But until fairly late in the war, when Goudsmith's team finally seized the scientists and they found the reactor and they really got a sense of the size of the effort, there was no way of knowing how far the Germans had gotten in the race for the atomic bomb. Now let's turn to Los Alamos, a project on an altogether different scale from the Nazi one, a project that in scope and implications was unparalleled in scientific and technical history. Los Alamos began as practically nothing. The site itself was a small private boys' school that was seized by the incipient project, the Manhattan Project, and then people were brought in from all over the country under conditions of enormous secrecy. So many of the young physicists who went there, I think the average age was about 24, had no idea really what they were getting into. And they were quite isolated. That was on purpose, both to prevent espionage and also, in case something went wrong, to give some space for this extremely dangerous work. And as the project got going in the beginning of 1942, really, it became a hub of scientific activity. To give you an idea of the scale, by the end of World War II, the nuclear weapons industry, as it had come to be, was roughly the size of the Detroit car industry, from nothing in 1941. So this was an extraordinarily rapid expansion. The problem that they faced was this. They had to know whether this fission process would, when a neutron hit a uranium nucleus of the right kind, would it generate not only the split nucleus, but also produce enough other neutrons to continue this. Not just one neutron, but at least two, so that you would start with one, that would create another neutron, but to have an extra one that would then make this process expand exponentially. So you would go from one splitting to 2 to 4 to 8 to 16 to 32 to 64. And that possibility needed to be explored. How many neutrons did a fission produce? What was the likelihood that a neutron would cause a nucleus to split apart? And how far would it penetrate in the material before that happened? These became questions of absolutely the first importance. American scientists began to suggest that people not publish about this. In fact, the Germans noticed that suddenly this most exciting of all discoveries went dark in the American press. One or two people did continue. Frederic Joliot-Curie in Paris, for instance, refused to block his research and published that the multiplication factor, one neutron would be 2.42 for uranium-235, which was promising for the continued possibility of a chain reaction. The amount of energy, as Heisenberg suspected, was clearly enormous, because the idea is really rather simple. It's that in a chemical reaction, you have an electron far from the nucleus. Most of ordinary matter is empty space, and the energy of attachment of that electron to the nucleus is what's responsible for all chemical processes, including explosions. Now, inside a nucleus, you are 10,000 times more compact than the radius from an electron to the nucleus. And more than that, you have, in the case of the uranium nucleus, not one lonely electron interacting with the core of the nucleus, but 92 protons all packed into a very small space. The combination of there being many more similarly charged particles that don't want to be together and to be that they're forced into an extremely small volume is what creates this enormous possibility for energy. If this thing could be broken in two, the two pieces of concentrated protons would fly apart with enormous energy, something like 100 million times the energy associated between an electron and a nucleus. 100 million times more energy per atom than you had in a chemical explosion. 100 million times more, for example, than TNT. What this meant, when calculated more carefully, was that a single kilogram of uranium could produce 20,000 tons of TNT. Something the size of a softball could wipe out a center city. It was thinking about these enormous energies and the possibilities that Germany might get there first that led certain key scientists, including Leo Szilard, Wigner, and others, to get Einstein to think about these questions. And Einstein, using the enormous influence that he had in virtue of being the world's most famous physicist by many orders of magnitude, then wrote a letter to the President of the United States, to President Roosevelt, and he said this: "Sir, some recent work by Enrico Fermi and Leo Szilard, which has been communicated to me in manuscript, leads me to expect that the element uranium may be turned into a new and important source of energy in the immediate future. Certain aspects of the situation which has arisen seem to call for watchfulness and, if necessary, quick action on the part of the administration. I believe, therefore, that it is my duty to bring to your attention the following facts and recommendations. In the course of the last 4 months, it has been made probable, through the work of Joliot in France, as well as Fermi and Szilard in America, that it may become possible to set up a nuclear chain reaction in a large mass of uranium, by which vast amounts of power and large quantities of new radium-like elements would be generated. Now it appears almost certain that this could be achieved in the immediate future. This new phenomenon would also lead to the construction of bombs, and it is conceivable, though much less certain, that extremely powerful bombs of a new type may thus be constructed. A single bomb of this type, carried by boat and exploded in a port, might very well destroy the whole port, together with some of the surrounding territory. However, such bombs might very well prove to be too heavy for transportation by air. The United States has only very poor ores of uranium and in moderate quantities. There is some good ore in Canada and the former Czechoslovakia, while the most important source of uranium is Belgian Congo. In view of this situation, you may think it desirable to have some permanent contact maintained between the administration and the group of physicists working on chain reactions in America. One possible way of achieving this might be for you to entrust with this task a person who has your confidence and who could perhaps serve in an unofficial capacity. This task might comprise the following: A, to approach government departments, keep them informed of further developments, and put forward recommendations for government action, giving particular attention to the problem of securing a supply of uranium ore for the United States. B. To speed up the experimental work, which at present being carried out within the limits of the budgets of university laboratories by providing funds, if such funds be required, through contacts with private persons who are willing to make contributions for this cause, and perhaps also by obtaining the cooperation of industrial laboratories which have the necessary equipment. I understand that Germany has actually stopped the sale of uranium from the Czechoslovakian mines, which she has taken over. That she should have taken such early action might perhaps be understood on the ground that the son of the German Undersecretary of State, von Weizsäcker, is attached to the Kaiser Wilhelm Institute in Berlin, where some of the American work on uranium is now being repeated. Very truly yours, Albert Einstein. Einstein came later in his life to regret that letter, to regret having pushed America towards the first step of the building of the atomic bomb. It took much more than Einstein's letter to get that project underway, but it indicates the importance that Einstein had as someone who could intervene with the President of the United States in this fundamental matter of war and peace. The technical problem was to keep the neutrons inside a mass of uranium and not to escape before they caused fission. And the question was, as it was for the Germans, how big does that mass of uranium need to be? If it got to be too big, it would be impossible to produce in the course of the war. If it was tons, as Heisenberg at first suspected, if it was small enough, it might actually form a bomb that could be delivered by airplane. It was important to distinguish, as the scientists in the United States quickly realized, between the fast processes, these prompt fissioning neutrons that went from one knocking apart of a nucleus to another, and the slow neutrons, or the delayed neutrons, that were involved in making just a reactor. The basic problem of making a bomb fell into two parts. At first, as in the German case, the American scientists thought that their only path forward was to take uranium, over 99% of which is uranium-238, that is to say, protons plus neutrons equals 238, and to extract that 0.7% of naturally occurring uranium that was a lighter form of uranium that only had 235 protons and neutrons. And if you could isolate this fissionable piece, that in sufficient quantity, you could make a bomb from it. The problem is that these two different forms of uranium act chemically exactly the same way, so no chemist can help you. The only way to separate them involved something physical that would separate a light form of this element from a heavy form. It's a very difficult task. But once you have the uranium-235, it becomes all too easy, all too tragically easy, to assemble it into a nuclear weapon. The other possibility was to design a weapon using plutonium-239. Now, plutonium is a substance which has a very long half-life compared to our lives. It's 24,000 years before half of it decays. But 24,000 years is as nothing compared to the age of the Earth, so there's none of it around from several billion years ago. That means you have to make it. Making it is difficult, and you need a reactor to do it. But once you make it inside the rods of uranium by bombarding them with neutrons, then it's easy to separate. That is to say, chemists can help. You can dissolve it in acid and separate out the plutonium, which is chemically different from the uranium. It's an exceedingly toxic substance. It requires a reactor to produce it. But once you have the plutonium-39, one additional problem arises, which is it's very hard to assemble quickly enough to detonate before little pieces of it begin to detonate and blow itself apart before it becomes a very consequential weapon. The process of making plutonium itself comes in stages, and at the fundamental level, what happens is you have a uranium nucleus, a neutron comes and gloms onto it. The neutron then decays into a proton and an electron. The electron flies away, and another particle, which we now know is the neutrino, flies away, and now with an added proton, the uranium is actually not uranium anymore. It's risen one stop on the periodic table and become neptunium. And neptunium can then get another proton and become plutonium. So it's a two-step process. You have to bombard these uranium rods with lots of neutrons, making some fraction of the uranium into neptunium and some neptunium into plutonium. But let's go back to this problem of separating the two kinds of uranium. You have to do it physically because, as I mentioned, chemists can't help you. It's the same stuff. It's the same element. One possibility is to heat it up, and the lighter atoms will get going faster than the heavier atoms. You can use that to separate the light from the heavy. Another possibility is to put it under pressure, and the lighter ones will make their way quickly through some sort of porous medium, and you can use that to get a higher ratio of the light stuff compared to the heavy stuff. Or you could send it around a kind of a racetrack using magnets to keep it in the circle, and then the lighter ones would fly off more quickly, and you can separate the heavy from the light in that way. 3 different methods. All were prosecuted to one degree or another in the war. All have been prosecuted to one degree or another after the war. We begin with uranium mining. It's a difficult, dangerous problem. It was what Einstein was worried about because for a while the United States didn't think it had very much uranium. In fact, it has enormous amounts of uranium. Canada, as Einstein knew, had a lot. The Belgian Congo had a lot. Uranium actually turns out to be pretty common. Then you take that uranium ore, you use acid and various things to extract, you crush it, and you get out this stuff called yellow cake, a uranium oxide, and then you take that and you mix it with another substance and you keep going, and eventually you get a gas called uranium hexafluoride, and that gas can then be used to do these various processes, to heat it up and use temperature changes to get out the lighter stuff, or you can spin it around really fast like a centrifuge, the way you separate out the heavy and light parts of blood, for example, or you can use this racetrack technique that I described earlier. So uranium hexafluoride is itself, it's a corrosive, difficult material. There's lots of it around. It's actually formed a big part of nuclear waste, which we'll talk about later. You can see here the size of the plants that are involved. You have the gaseous diffusion plant at Oak Ridge, Tennessee. It's one of the biggest industrial plants ever made. You have the thermal plants. They're also gigantic. You have these electromagnetic separation facilities. They're also a big operation. In fact, they ended up using so much of the silver supply of the United States to run their magnets that the government was forced to issue steel nickels. If you've ever seen a steel nickel from the war years, it's because of the atomic bomb. All of these processes combined to produce enormous effort that ended up costing about $2 billion and ran from 1942 to 1945. In 1945, the first of these weapons was tested, and the uranium bomb was considered so incredibly straightforward that it was never tested, that there was seen to be no reason to test a bomb. The first uranium bomb that ever exploded in the history of the world was the one over Hiroshima. The bomb that was used over Nagasaki was rather different. This was a complicated problem. You had to get the plutonium to come in very fast into and compress it from a sort of grapefruit size to a golf ball size. And that was a tremendously difficult problem that took very great calculations and some of the work of both the earliest computers and some of the great mathematical physicists, applied mathematicians that the world had to offer. So that was the one that was tested. And here I think it's worth seeing a clip of a wonderful documentary film by John Else as he describes that moment, as he talks to the people who were there for that first detonation of a Nagasaki-type plutonium bomb. But the legacy of making plutonium is still with us today. The sites, the reactors at Savannah River in South Carolina or of Hanford in Washington state are still enormous buildings, canyons as they're called, in which the uranium rods that have been exposed to massive numbers of neutrons are dunked into boiling nitric acid, and this horrible mess then eventually dissolves the rods. Those are filtered out into the plutonium separated and eventually assembled into the plutonium bombs that formed part of the arsenal. What I'd like to do next is to think in a slightly orthogonal or unusual way about what happened to these bombs as they were let loose over Japan, and to take as an example not just the pictures, which I think many of you will have seen of the detonations over Nagasaki and Hiroshima and some of the legacy of destruction that they left, but also some testimony from some of the people who were there. And for that, I'd like to have join me in conversation Hilary Shute, who is one of the best scholars at work today on the graphic novel and the way it was used by one of the people who was born in Hiroshima and who used his writing and drawing over the course of a lifetime to try to understand what had happened there. Welcome, Hilary. This is Hilary Shute, who's an expert on graphic novels and graphic narratives of a variety of kinds at the University of Chicago in the English department. Hilary, I was hoping that today we could talk about something that you've worked on a lot, which is the development of comics as a register in which expressions of concern and of witnessing have expressed themselves, especially with regard to nuclear matters, and even more particularly with the remarkable figure Keiji Nakazawa, who has really done so much to transform the Japanese understanding of what happened at Hiroshima and Nagasaki.
Sure. So Keiji Nakazawa's work, Barefoot Gen, is one of the most famous manga in Japanese history. It sold over 8 million copies. This work is a sort of cultural truth in Japan. And I'm interested in Nakazawa because he was the first person to do so-called atomic bomb manga. So this is a genre that he created. Even saying the genre of atomic bomb manga is to me an interesting and rich idea. So Keiji Nakazawa himself is a survivor of Hiroshima. So he was 6 years old when the atomic bomb dropped, and he was on his way to school less than a mile from where the bomb hit. And he was standing next to a cement wall with a line of other children, and he was basically himself unscathed when the bomb hit, except for superficial injuries. So Keiji Nakazawa didn't decide to become a cartoonist until the 60s, and at that point he moved from Hiroshima to Tokyo. And he kept trying to get at this story from a fictional point of view. Culturally, it was very unusual for hibakusha, survivors of the atomic bomb, to speak out about their experiences.
It was quite a taboo, in fact, a kind of shunning of the hibukasha, right?
There was absolutely a shunning. So officially, there was U.S. Imposed censorship on discussion about the atomic bomb, but this was also taken on by the Japanese themselves. So there was a cultural and official U.S. and Japanese censorship, and once the official U.S. censorship ended, culturally, the community enforced it. Hibakusha were shunned, they were stigmatized, people didn't want their kids to play with kids who were survivors. There was an incredible stigma. And we see this in the fascinating way that he started to try to do this work. So even when he did stories about survivors in a fictional context, these stories were considered so politically radical that they were shunted off from the mainstream. So his first attempt at this was a story called Pelted by Black Rain, a very evocative title. He did a story called Suddenly One Day, also about the bomb, fictional. And this story elicited an enormous response. He got hundreds and hundreds of letters from people telling him how much the story had meant to them and how they didn't even understand, just simply factually, some of the parameters of what had happened that day that were outlined in this story. So at that point, he decided to make a go at doing an autobiographical story about being a survivor. And that resulted in Ore wa Mita. In the US, it's called I Saw It, which came out as a standalone comic book in 1972. And so this was the first autobiographical comics work about the atomic bomb. And it was also the first significant cultural work by a survivor that dared to take on the physical suffering and dared to take on the emperor system and be critical of the Japanese in addition to being critical of the Americans. So it was a major work and a taboo-shattering work on many different fronts.
The story is unbelievably affecting when one reads it even now, half a century later. I mean, just his mother saw the father and the brother pinned under the house, and eventually fire overcame them and she had to leave and they burned to death.
I mean, it's devastating. I'm getting goosebumps just thinking about it. So his mother, Kaimi Nakazawa, was actually pulled away from the house before the house collapsed in flames by a neighbor who physically dragged her away as she was trying to save her husband and her son and her daughter from the wreckage of this house. It's a devastating story. And she actually died in 1966 from leukemia, the leukemia that was so common to survivors of the atomic bomb. And it was her death that spurred Keiji Nakazawa to do stories about the bomb. And one of the details that I've always found very moving is the fact that he was so upset by the fact that there were no bones left over when she was cremated, as there typically are, that made him decide that he would do comics about the atomic bomb.
As a way of preserving something from that.
As a way of preserving something, because he was so devastated and so enraged that the bomb had even deprived him of his mother's bones, that even her bones were so weak that they all became ashes when she was cremated, that there was nothing solid, not even a tiny piece of bone that he had left of his mother.
For generations after the bomb, most Americans' perception or understanding of what had happened from the point of view of the Japanese came through John Hersey's book, Hiroshima, where he followed 6 people and what happened to them. But there's something, seems to me, of a sea change that happens when the voice isn't transmitted through a Western American writer, and Nakazawa's own witnessing becomes the primary form of expression. There's also a change of medium from a book to something that's graphically presented. Could you sketch what this object is? I want to dig in and really look at the way the page is laid out, the way the graphics work.
This story has a frame narrative where Keiji Nakazawa is an adult explaining to readers how he came to be a cartoonist doing this kind of work. And so we see him in the beginning in Tokyo, rueing that his mother was never able to ever visit Tokyo, which is something she had always wanted to do. So he makes it a sort of a Bildungsroman in a way. Here I am as an adult, and now I'm going to go back and show you what I was like as a child and how I got to be, the artist I am today. First, we get this, I think, really key scene in which he says, "I am Keiji Nakazawa, born in Hiroshima City, March 1939, third son out of 5 kids." So what's key here is that he is establishing that this is a first-person narrative, and he's taking responsibility for it as a work of autobiography. This was the unprecedented part, right? To have this kind of history and to have it be framed as autobiography. And what's also key here is that he is establishing his identity as a son, which is something we also see in famous works like Art Spiegelman's Mouse that came out in its short version around the same time as I saw it. And then the page goes back to 1941 and an air raid. And here we see his mother's feet tramping, and I love that we get the sound effect here that says tramp, up the stairs in an echo of his feet here. So then we're back in the past, from the 60s to the 40s, and we have these, I think, very moving scenes of everyday family life. So here's a scene of the family having dinner. We learn that there isn't a lot of food in the household. Here we have a scene of Keiji visiting his father as his father is working and asking him to please teach him how to draw a soldier. We get a sense of the kind of rhythms of their everyday life. He says here, my happiest times were catching grasshoppers, right? So we get a sense of the slowness of their life in addition to the big events that they were dealing with, like the war. So then the book takes us to 8:15 a.m. And what we get here is a panel that is actually representing the explosion.
This is August 7th, 1945.
Right. Many of the survivors described their experience of the bomb as a noiseless flash. People's faces are starting to be framed in only black and white. We have a sort of expressionistic view of a purple tree flying through the air, broken apart, and then the panel goes all black. There hadn't been imagery like this in any other drawn work. These images of people with their skin dripping off of their bodies, this is the sort of signature of this work. This very hard to look at, grotesque, almost cartoonishly grotesque set of images of people with their skin burned off and people with their skin dripping and hanging from their bodies. What we get here is a kind of conflation of a popular idiom with non-genre work about witnessing. So when he says here, everybody's turned into monsters, these people look like you might expect monsters to look like in a science fiction manga series.
It's also transmitted through the vocabulary of a child. I mean,
Right.
a monster was
Right.
something that children are afraid of.
The book is inhabiting the kind of discursive position of the child, which is very powerful and very moving. And that he drew it so bluntly, one might say, in the conventional popular idiom of manga, but depicting these grotesque and horrifying realities, made people wonder about just how upsetting these images were. You know, it's like it's science fiction, but it's not science fiction, it's reality. The kind of gap that's implied here between a conventional, popular, violent science fiction story and the fact that this is being framed as what he saw with his own eyes was part of what made this work such an unusual and such an upsetting work. One way that I've liked to try to understand this is that he created himself a new kind of visual idiom that to me is about defamiliarizing received images of the war. These are images that are grotesque, they're on the ground, they're inhabiting the kind of exaggeration that would seem to be a flourish, except in this case, he's claiming it as, I saw this. In a way, people talk often of trauma as frame breaking, that it produces experiences that can't be contained, and trying to express those experiences is so often form shattering and genre shattering for that very reason, because trauma is, by definition, a kind of excessive experience. It's an experience that has to be deferred, can't be understood, in the instant. trauma in this instance is helping to create these new forms. That this is a form that's working in this sort of grotesque, exaggerated idiom, but it's also a form that's documenting with that vocabulary and expanding that vocabulary. This is never something that can be contained. And I think with the comics frames, we constantly get a sense of the tension between what can be contained within the frame and what is outside of the frame and can't be contained within the frame, both in terms of historical realities and in terms of the burden of expressing those realities. So comics is this constant counterpoint between presence and absence. So it's always making you aware of what can be pictured and what can't be pictured, what can be put in the frame and what makes the frame possible but can't exist within the frame.
And what can be done in words and what can be done wordlessly through images, and then what their combination does.
Right, so in comics, the words and the images don't match up the way people often think they do. People often think that comics is an illustrative form in which there's a narrative track and then the pictures match the narrative. Actually, comics is a form that's all about disjunct. So the words are doing one thing often, and the pictures are doing another thing. We also have the disjunct between what we see in the frame and what we don't see in the gutter. So there's a constant kind of rhythm in comics between what you know and what you can't know. And so that's one of the reasons that it's such a powerful form for trying to express traumatic histories.
Thank you enormously, Hilary, for this really interesting discussion. And I should say that your book, Graphic Women, is a terrific entry point into thinking about questions of trauma and the graphic novel.
Thank you. It's been so interesting to think about comics in this context today.
What we've sketched, only in part of course, is the development of the atomic bomb in its two first forms, the uranium-235 bomb and the plutonium bomb. But it was not just a technical achievement and not just a military event either. It transformed world culture. It transformed the way modern nation states have seen their relationship to power and the organization of the confrontation that constituted the Cold War in so many aspects. Just to give you one idea, over the course of the Cold War, several times $1 trillion was spent by the United States and a comparable amount by the Soviets. The creation of nuclear weapons and the nuclear weapon establishment transformed the land. It transformed the relationship of science and the state. It led to the contract system and the relationship between the government and scientific research in universities and industry. It transformed the position of scientists in society. It led to a cultural impact that we'll be unpacking for a very long time to come, as people in every city in the former Soviet Union, in the United States, in Europe, and beyond, began to think that their cities, their lives, could be ended in a millionth of a second with the explosion of a nuclear weapon. The implications for culture, for our understanding of the precariousness of our perch on the world, the escalation of nuclear weapons from the atomic bomb to hydrogen bombs to nuclear-tipped missiles with many weapons on each one, submarine-borne and airborne, missile-borne, all of these escalating, spiraling advances in nuclear weapons, their proliferation to many more states, became a part of how we understand the late 20th and early 21st century. It's our task in the next lecture to at least get a glimpse of the implications of this utter alteration of the relationship of science to the world in which we live.